Okay, so let's. This is one of the last topics in related to differential amplifiers. We had started this in the last lecture. I'll quickly go over it. And so mismatch is something that I said is extremely important whenever you require two identical transistors for proper functioning of the circuit. And if you recall, we said that suppose you had a wafer and you made two transistors close to each other, a pair of transistors, and you made it at several places on the wafer, right, all over the wafer. And what you would find is that even though you're using the same process for making the transistors, the threshold voltage of this transistor and the threshold voltage of this transistor would in general be different. And if we measure the delta VT, that is, let's say the bottom one is transistor M1 and the upper one is transistor M2. So if we measure the threshold voltage difference, which is delta VT, and we plot it. So we measure the threshold voltage difference here and here and here. So let's say we have some 1,000 transistors, 1,000 pair of transistors, and you measure delta VT and you plot it. What you would get is a bell curve like this here, which shows that the threshold voltages are in general different of the two transistors, and average may be zero, mean may be zero here, but then you would have a certain amount of variance which is there. So the point is that two transistors in general fabricated close to each other will have a threshold voltage difference. Now, they will have a threshold voltage difference. They will also have a difference in, for example, mobility. So the beta, the K and W by L, the beta parameter will also vary. So there are a lot of, so two major effects. One is VT, which will vary, and the other one is beta of a transistor. The Kn, as all of you know, depends on mobility, and mobility would also vary as you go from one side to the other side here. All right. And so we said one of the important trends that people have observed is that if I look at the variance of the threshold voltage change, the variance goes as, there's a constant factor, it goes as 1 over area of the transistor. The larger the area of the transistor, the smaller the variance that is there here. And so that is one dependence, the area dependence that you see here. And the other dependence is the effective distance between the two transistors here. So there's a term which depends on the distance between the two transistors, and there's a term which depends on the size of the transistors here, inversely proportional to the size here. So if you want to keep minimize the mismatch, we know what we have to do, make areas large. This is something that you can't touch. You can ask a process engineer to give you a very small value of AVT, but this is something, once you choose the technology, AVT is fixed, SVT is fixed. So what is under your control is the size of the transistors and the separation between them. Okay. And these are some typical values. This is the older technology, some typical values are given here. All right. And people have observed this kind of a trend by actually measuring the variance and plotting it against 1 by W, plotting it versus D. So empirically, they have verified that a relationship like this is fairly reasonable. Okay. All right. Now, besides VT that I talked about, the other parameter which varies is, as I said, beta. Beta depends on mobility, beta depends on other things, and this also varies. And this variation is also something similar. So the change delta beta by beta has a variance, which means what? If you measure beta 1 and beta 2 of the two transistors, calculate delta beta, and you plot delta beta by beta here. And you will find that also has a bell curve, that also has a variance. And that also goes as 1 by area here and varies with the distance here. Okay, and similar parameters can be found out empirically. So what you do is you measure several pairs of transistors, plot it out, and check how it goes with D and how it goes with area, and that's how you obtain the parameter A beta and S beta. All right. So we assume that these values are given to you. So we can see the consequence. So if I look at ID, beta by 2 VGS minus VT squared. So as a consequence of mismatch in beta and as a consequence of mismatch in VT, two transistors, neighboring transistors, biased in exactly the same manner, will have a mismatch in ID. And that is fairly easy to see. Delta ID, as you can see here, will be delta beta by 2 VGS minus VT squared plus beta so much here. And one can obtain a percentage change in ID, delta ID by ID. So that is delta beta by beta plus 2 VGS minus VT times delta VT. right? So it has the percentage change in current has two contributions. One is from changes in beta, and the other ones are changes in VT here. And if we assume that this delta VT is a random variable, and delta beta by beta is also random variable, if you assume that they are independent, they may not be, but if you assume that they're independent, then the variance will simply add up. Sigma square of delta ID by ID will be sigma square variance of this one plus variance of this one. So if you assume that these two are independent, right? But it may not be. The whatever is causing variations in mobility may cause variations in threshold voltage also. So that one has to be a little bit careful here. But a simple view would be the variance in delta ID by ID is simply the sum of the variance here at 4 by VGS minus VT square. All right. So this tells you that if you want very good matching between the current, of course, as I said, you have to keep area large and the distance between the transistors small. But apart from that, you can also see your biasing affects it. If you keep VGS minus VT large, then this term becomes smaller here. So this is what we call as VGS minus VT. We call it as gate overdrive, is the saturation voltage of a transistor. So if you keep this large, then you will obtain smaller overall mismatch between the currents of the two transistors that you see here. Okay. All right. So this is what we had discussed earlier. Say I have a differential pair, two transistors M1 and M2. The usual way in which I would, or a simple way in which I would fabricate is make one transistor here, make another transistor here, then you connect S1 and S2. So this would be a normal way, but what would happen is, I'm not showing here, this is I can calculate the sigma square, and for a moment, not talking about D, just taking the first term. So first term, because I don't have right now the value of D, it depends on the layout, and from there we'll have to figure it out. So if I just take the first term, the standard deviation is 4.1 millivolt. The standard deviation of delta beta by beta I can also calculate, given that W by L's are there, and sigma of percentage change in current is 0.019, and so it's basically 0.019 or 4.2% when you have VGS minus VT. Gate overdrive is 0.2 volt. And remember, what is of interest is not just sigma. At least 3 sigma is what you would take, right? Most of your devices will lie between 3 sigma here. So 3 sigma is 12.6% here. All right. So it's a fairly large. So what I'm showing is I just took 2 transistors 10 by 1, and I'm showing that 3 sigma for this is 12.6%. So it's a fairly large change. Fairly large change in current that one is talking about here. The other thing that you see here is I'm also pointing out the trade-off between accuracy and power. Which trade-off that accuracy and power is coming by looking at this expression here. This tells us that if you want to minimize sigma, delta ID by ID, what you should do is, of course, aside from area and distance and all that, as I said, VGS minus VT you keep large. Now what would happen is you keep VGS minus VT large, area is also large. What will happen to the currents flowing? The currents would also become large here. So that, and if the currents are large, then of course there's more dissipation in the, more power drawn from the circuit here. So what you see here is there is a sort of a trade-off you can see between accuracy. Accuracy will be related to mismatch, accuracy and power. If you want to achieve highly accurate circuit, you'll have to spend more power here. So it's just hinting towards a trade-off that you may see in circuits where accuracy depends on the mismatch between the transistors here. All right, so this is what we had discussed in the last lecture, that this is the simple way of making 2 transistors M1 and M2. But it's not a very good way because the distance between the 2 transistors is large. And we saw that this may be better, more compact. Here you have 2 separate sources. Here they share the source. D1 is here and D2 is here. So it's better, more compact. The distance between the 2 transistors is also smaller here. But a better strategy is that you split a transistor into 2 parts at least. D1, one part is here. M1, one part of M1 is here. Another part of M1 is here. one part of M2 is here, another part of M2 is here, and this is what it shows. So by this means what you do is the centroid of M1 lies here, the centroid of M2 also lies here. Effective distance between the two transistors becomes 0, and thereby you minimize the mismatch between the two transistors here. So I was emphasizing that one uses a common centroid layout here. If the transistor is large, then you may want to split it into several components here. Here it shows 4, M1, 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 and M1 here. So one transistor is split into 4 segments, and the drain of M1, all these M1s will be shorted. The source of all these M1s will be shorted, and gate will also be shorted here. So by splitting, one is able to achieve a common centroid, distance equal to 0. But you note that I will have to do more of metal lines and connections and all of that. So that's the price that I will end up paying here, right? Okay. Now, let's examine the effect of mismatches in a little bit more detail here. So through simulation, focus on this particular, I want to illustrate a few things. So this is a differential pair with current mirror load, right? So for it is biased here through minus 2.408, bias voltage is here. There's a negative supply, positive supply here. And the body is also connected to the negative supply here. So note, no input is applied. This is ground and this is ground, right? So, and right now I'm assuming all threshold voltages are the same, right? No mismatches. All betas, all threshold voltages, everything is the same. And therefore, what you note here is the voltage that you see here is 2.209 and the voltage here is 2.209. Remember, that's where you take the output voltage here at this node, right? Output voltage is taken here at this point. So a circuit is symmetrical. You can see 2.2, 2.2 here. And we've already seen that even though this is shorted, as long as the transistors are identical, the two voltages are the same, right? So that's when no mismatch is there. Now I'm going to create a mismatch between the two. See what happens. The threshold voltage of transistor 2 is still 690. The threshold voltage of transistor 1, I've made it a little smaller, 5 millivolts smaller. Now can you see? This is 2.206. This is same as earlier. This was 2.209 is almost 2.20 this thing. This has gone to 3.088. Why has this happened? Can you all understand that this has gone a little higher? Not a little higher. In fact, the voltage here has changed by 1 volt. Earlier it was 2.09. Was it 2.09? 2.209. All right. So 2.209. So it's a little less than 1 volt here. So voltage here has increased by roughly 2.2, so about 0.8 volt. Okay. Why has it increased? Can you all see that? If the threshold voltages were the same, the currents here would have been the same. Threshold voltage is a little smaller here. Current here becomes a little larger, right? And the current here then obviously will become a little smaller. Why should the voltage increase? How should you understand this? Why should the voltage increase? Well, VGS of both the transistors is the same, and you're wanting lesser current here as compared to this, which means its source to drain voltage should be smaller. Source to drain voltage should be smaller. So, and the only way for this is to go up. That's one way of looking at it. What is the other way of looking? Other way of looking at the same thing? Note that what affects the current is VGS minus VT. So VT has changed, but I can sort of simulate the effect of VT by changing VGS. Is the same thing because they come as VGS minus VT. So a change in VT can also be mimicked by a change in VGS. So a 5 millivolt change in VT1, how would I simulate it? Suppose I said VTs of both are the same. How would I simulate the effect of this? By saying VGS of this transistor is a little higher than this one by 5 millivolts. So it can be done by attaching a source here, 5 millivolt. Now, when you attach a source here of 5 millivolt, what does it do to the output? It gets amplified, right? And what is the phase difference between this and this? 0. So when you apply a voltage here, so effect of VT change is same as a, you can think of, which we'll see, is by attaching a source, a voltage at the input here. It can be simulated. And this voltage will get multiplied by the gain and will appear over here. Okay? Alright, so that's VT1 and VT2. Look at this one. VT1 has now increased. Earlier it was a little lower by 5 millivolts. Now it's a little larger than 5 millivolts. Obviously, the current here will become a little smaller, current here will become a little larger, and that's reflected in delta V0 of minus 0.84. Right? So that's there. Now, so these are the changes that occur because of changes in VT. Now, what I'm saying is the following. Note that, keep this in mind here. 2.2 and 1.249. That's because of change in VT. Right? There is no input here. Now, the same effect I can create as far as the output is concerned, same effect I can create by keeping VT as the same. The VT of both are same, but by connecting a source here of minus 5 millivolt. Note that it also results in 1.249. Same effect can be created by, there's no mismatch, nothing, everything is ideal, but by attaching a voltage at the input here. So what does this tell us? That the effect of mismatches can be what? Can be compensated by attaching a voltage here. Or in other words, what I can also say is the following. Here is a differential pair, a realistic differential pair with all the mismatches that is there. And obviously it will suffer from that. Now what can I say the following? That I can consider now a differential pair with no mismatches, and the effect of all the mismatches is lumped in this parameter. Remember what we had done? We had said that here is a circuit with noises. And now I can take all the noise and put it at the input, and the rest of the circuit is noise free. It's the same idea that is being done here, that all the effects of mismatches between M1, M2, M3, M4, everything that is there is all lumped up here. And the differential pair now itself is perfect, right? And all the mismatch effects have been incorporated here. So what are we saying? The effect of mismatch is being described in terms of a parameter called input offset voltage. Input offset voltage here. Because what does it do is, note that if the differential pair were perfect, the output would have been whatever its normal value is. Because of the effect of this voltage, what will happen now? The output will go somewhere else here. With the same thing that the mismatch does. The output departs from its normal value. The output goes up or down or whatever below its normal expected value here. The same thing happens as a result of VOS. So all the effects of mismatches and everything is described in terms of a parameter called input offset voltage. Right? So this becomes then a important parameter of a differential pair. How much is this input offset voltage? Right? So what we have to do is, you can see here input offset voltage will be determined by at least 4 factors here. One is the difference in the VT of M1 and M2. The other, which is delta VTN, N-type. The other one is difference in VT of M3, M4, which is delta VTP. Difference in beta of M1 and M2. And difference in beta of M3 and M4. So 4 factors you can see here. They are going to contribute to input offset voltage. Alright, so let's calculate these effect of those factors here, and let's obtain an expression for input offset voltage here. Alright, so the way I'm going to do is the following. I'm going to consider one at a time. And basically, one at a time, and we are going to do a small signal analysis because the effects are small in nature. The mismatch between the two transistors M1 and M2 is small in nature, so I can use small signal analysis. Okay? Alright, so the idea is as follows. I'm considering a input offset voltage due to M1, M2 mismatch. Right? So the idea is as follows, that threshold voltage of M1 and M2 are different, and therefore the current ID1 and ID2 will be different. Right? Now what I'm saying is, I'm attaching a source here which is minus VOS. Now when I attach minus VOS, what will it do? Note that if VOS was not there, ID1 will be different from ID2. Right? Now I'm attaching a source minus VOS. What will it do? It will cancel the effect of mismatch and make ID1 equal to ID2. right? So that's the idea of VOS. VOS simulates the effect of mismatch. And now I'm putting minus VOS. So it will cancel the effect. So what will happen to ID1 and ID2? Despite the mismatch, they will remain the same. Okay? So keep that in mind. So now this is ID, which is IS by 2, beta by 2 VGS minus VT square. I'm writing delta ID, right? So now note in this overall circuit, delta ID will be delta IDS by delta beta 1 times delta beta 1 here. Delta IDS by delta differential with respect to VT minus delta IDS delta VGS by VOS. Correct? This is VGS of this particular transistor here. Okay? And now what I'm saying is delta IDS is 0. Delta IDS is 0 here. That there is no change. Okay? There's no change. And therefore, we obtain an effect of input offset voltage due to mismatches in beta of the two transistors and also the mismatch between threshold voltage of the two transistors. Okay? Agreed? So all that we said was delta IDS is 0 because we have attached minus VOS. If I had not put VOS, then there would have been a change in ID. Okay? So we put VOS. So we get the effect of mismatches between M1 and M2. Let's look at the effect of mismatch due to the mismatch between the threshold voltage of M3 and M4. And I've put it over here. Threshold voltage is different between the two. And I'm simulating it by saying threshold voltage of M3 and M4 are same, but by putting a voltage source here. Can it simulate the effect? Note, M3 and M4 threshold voltages are different, correct? But I'm saying, let's assume that the threshold voltages are the same and putting an external source which is equal to delta VT. Because if the threshold voltages are different between M3 and M4, what does it mean? The current is affected by VSG minus VTP, right? And so VSG minus VTP. VSG is the same for both of them. And what is different is VTP. Now what will happen is I've made VTP same, but what have I done? VSG different. So it's the same thing, right? So instead of talking about VTP different, I've taken VTP out and put it as an external source. Alright, and now saying threshold voltages are the same. Is the same effect? Okay, so now what I have to find out is what is this delta VTP does to my output? Okay, how do I, what does this delta VTP do to my output? And then I will try to obtain the same effect due to a input offset voltage here. And that's how I will get the phenomena here. So what I'm trying to do now is this delta VTP is considered as a small signal source. And I'm doing a small signal analysis here. This is ground. We all know this is 1 by GM3. And the way we find out the effect on output is by calculating Norton's current. And the Norton's resistance we already know is R02 parallel R04. Alright. So Norton's current here. How do I find Norton's current now? What do I do? Now, the approximation that I make is note that this is delta VTP. This point is connected through 1 by GM to ground. 1 by GM can be considered as very small. So its effect is as if this is connected to ground. So what is the net gate to source voltage? VTP. And how much should the current flow? Can I say IN will be equal to GM4 times delta VTP? Because how much is the current that flows? Current that flows through a transistor is GM VGS plus VDS by R0. How much is VDS? This is ground and this is ground. So the second term is not there. So I left with GM4 delta VT. So this source that you see here will cause a Norton's current of GM4 times delta VT. Now this one I can counteract by attaching a VOS. Suppose I put a VOS here, minus VOS here. What kind of a current will it cause? Minus GM1 VOS. And the two have to counteract with each other. So its effect can be simulated by this much. Because the net Norton's current, if net Norton's current then becomes 0. So what I'm saying is this delta VTP is there. Take this source out, ground out, and put a minus VOS. If this is minus VOS, what is its contribution to IN? We have already seen is equal to GM1 times VOS. And therefore, net IN becomes minus GM1 VOS plus GM4 delta VTP. And we are saying net Norton's current is 0. because it's being cancelled by minus VOS. So we get a value of VOS here. So this VOS is due to mismatch between the threshold voltage of M3 and M4. Okay. That's how we obtain the contribution here. So like that, we have already obtained a VOS due to mismatch between M1 and M2. We have obtained a threshold VOS due to mismatch between M3 and M4, the threshold voltage mismatch. Next thing is we are left with beta 3 is less than beta 4. Alright. Beta 3 of this transistor is different from beta 4. I'm saying the effect can again be simulated by attaching a source called delta VGS. If beta of two transistors are different, what will it do? Current of the two transistors are different. The same effect can be simulated by saying VGS of the two transistors are different. How do I do that? Note here ID is beta by 2 VGS minus VT. Delta ID is delta ID by beta, delta VGS equal to 0. So the effect of change in beta can be simulated by a change in VGS. And what is that change in VGS? Delta ID by so much here. Okay. So instead of doing the same calculation now with different betas, what we are saying is the effect of beta change can be simulated by a change in VGS. And we've already seen what this VGS results in offset voltage, right? So any change in delta beta by beta results in a change in VGS here. And now we say V offset will be equal to whatever we had calculated here earlier. Remember beta 4 by beta 1, the same factor we multiplied. Beta 4 by beta 1. So we get the effect of beta 3 and beta 4 being different, and we get what is the contribution to threshold offset voltage by beta 3 being different from beta 4. So now we have seen all four factors. What you need to do is add them all up. So add the effects of threshold voltage mismatch, beta 1 mismatch. You add all of them up together and you obtain an expression for input offset voltage. So these are the factors that affect your input offset voltage of a differential pair. These are the same factors that will affect the input offset voltage of your op-amp. Because what will happen is differential pair has, matching is required. After that stage, you won't have a stage where matching is required. Right? Because after that, you will have a common source amplifier, matching is not required, and an output stage and all that. There's no matching effect after that. So offset voltage is determined by differential pair. And the same expression will be used for op-amp also. So now you see, if you want a small offset voltage, what do you have to do? Note, you would like to make all these delta beta 1 by beta 1, delta beta 3 by beta 3, delta VT and delta VTP small. All that is telling you is large size. Keep areas large and automatically the mismatches become small here. Large sizes make D0 by using a common centroid layer. If you do all of that, then what do you do to biasing? Small ISS is what it says is biasing. Keep this small to keep input offset voltage small. Alright, so these are the factors. All the factors are in front of you as to how you affect the input offset voltage. Alright. Okay, so